for the guest professor staying with us for the next month, until Easter, I guess. Serhiy has a quite interesting CV. He did his studies of physics originally in Moscow, and then his PhD in mathematics at the Academy of Science, National Academy of Science in Ukraine. And he got his PhD in 1997 with work on the Chua oscillator. After that, he had quite a lot of research stays that I can't go over in all detail. But he has been for a long time, I think meanwhile 12 years at Berlin, both at the Weierstrass Institute, that many of you might know as well. It's a mathematical institute in the heart of Berlin. And at the Humboldt University, where he has been first as a postdoctoral scientist, then as a guest professor and junior research group leader. He has received quite a lot of awards and recognitions. I picked two that I find remarkable. One might not be one that you would have chosen yourself, but he has been last year rewarded, or this year rewarded, Outstanding Referee for Physical Review Letters. That's a nice title to achieve as well. And he's a member of the executive board of one of these prestigious collaborative research centers. It's one of the most prestigious funding schemes in Germany, in Berlin. This is one on complex networks, right? Do you know what the title is?
Control nonlinear self-organized system. I don't remember.
You should know.
It's nonlinear dynamics.
Serhiy is a very dear colleague for a long time, and we have been together already struggling to find out all the mysteries of delay systems. So he has been working on delay systems for a long time, on control of dynamical systems, and a lot on synchronization of dynamical systems. And today he will tell us about the latest revelations, what mysteries can be extracted from delay systems. He will tell us about the occurrence of defects and turbulence in systems with two delays. We're very, very happy to have you here. And as I said, he'll be here with us for the coming months, so whoever would like to interact with him, you can find him in office number 105.
Thank you very much, Ingo, for the introduction and for invitation to stay here. It's a very nice and creative place, very strong group to collaborate with, and I'm very happy about that. Thank you very much for coming. And so today I would like to talk about systems with two delays and how one can observe in systems with two delays turbulence or defects. This is a joint work with Giacomelli from Florence. So, works hopefully.
You switch it on?
Batteries like
French. Yes.
Switch on the laser works.
the computer froze.
Doesn't rest.
The clock is still
So
running.
the first delay is already in the morning. Okay. So hopefully it's not so long. But so this is how what kind of systems we consider, just very roughly. There is some oscillator, a system which can oscillate, and there are two delayed feedbacks. Tau 1 we assume is a long delayed feedback. Long means that the delay time is larger than characteristic time scale of the system. And Tau 2 is much larger than Tau 1. So this is a setup for a general. So main ingredients, two delayed feedbacks, delays are large, and it's important that this system can oscillate. One can imagine the following experimental system. We did not do this. We computed numerically using the Kobayashi model. The system would be some laser, semiconductor lasers with two delayed feedback, Tau 1 and Tau we considered numerically the generalized Kobayashi model, which is, in the classical case, this is just one delayed feedback. We studied the second delayed feedback. So the outline of my talk is the following. I firstly consider just a simple model, minimal model, which is a Stewart-Landau oscillator with two delayed feedback, where I show how one can study stability of the steady state, the spectrum of eigenvalues, and then how one can map the solutions into the solutions of some PDE, partial differential equation, special temporal representation, and then show how spiral defects and defect turbulence appear in such system, and then show that the same effect appear also in generalized Kobayashi model. So the minimal model. This is just this equation, which is where z is a complex variable. It's without delayed feedback terms. It's a normal form for Hopf bifurcation, so it can oscillate. That is a complex of two components, and it's appended with two delayed feedbacks, this one and this one, linearly. So it's kind of very simple system. And if we just use our numerical algorithm, and look numerically what happens in this model, one can see very often such behavior. So delays you see here quite large. So tau 1 is 100, tau 2 is 10,000, and one can see numerically such a behavior which repeats itself somehow. These are very comparably fast oscillations. You see these are sharp peaks, but they are smooth. You can zoom it and then see some smooth oscillations. And then on the top of this, you see some slow oscillations which have some different time scale. So this funny behavior one can see robustly in this system. On the other hand, if we change parameters, we can see also this behavior, which is more erratic, more chaotic, and again, different time scales and different behaviors. And again, this was robust in the system, and in fact, what I'm going to show is that these two behaviors can be mapped. So this will be mapped to this. I will explain this more specifically. What does it mean? And this will be a spiral defect, and such behavior will be mapped to defects chaos or defect turbulence regime, and I will explain what does it mean. So in some sense, I will show that this behavior and this can be mapped to a behavior of some specially extended system, or some partial differential equation on a two-dimensional domain. So this is two spatial variables. And even more, these are two spatial variables. These patterns will evolve with time, so that we will see some evolution, temporal evolution of patterns. I will show you now in movies how these patterns look like finally, evolution of these patterns, and then I explain in more detail. So the next slide will be just some final result which we come at the end. But finally, this solution, which looks like that, will be, if we appropriately map it into a special extended system, will look like this. So this is an absolute value, and you see there are 2 points where absolute value goes to 0. The blue goes to 0. So these are defects. And looking at the real part, one can see that these are really spiral defects. And this is what one expects modeling some special temporal systems, Ginzburg-Landau. But in fact, this is just the solutions of our delay system. I will explain what does it mean. Another case, this behavior with this was more erratic, more chaotic, will look like this. This is an evolution of a pattern in such a case, and this will be turbulence of defects. And this is more regular, of course, than the previous one. So you see that this mapping it looks like this, and I want to explain how we do it, how we obtain this relation. So please ask me questions, interrupt me any time when I'm saying something not very clear. So let's start from the very beginning, and we start from the stability of a linear system, linearized, close to zero state. So this is a linearization where the nonlinear term is dropped. So we have just three the linear terms, the instantaneous, tau1 feedback, tau2 feedback. For simplicity, or not for simplicity, but generically, we can always write tau1 and tau2 in such a form in order to show that they act on different time scales. For some reasons, there is no line. This is 1 divided by epsilon. This is kappa divided by epsilon squared. So if epsilon is a small parameter, then tau1 is large, yes, and tau2 will be even larger. So this is somehow how one can formalize the fact that tau1 is large and tau2 is even larger. Okay, and if we look at this equation, for this eigenvalues, we obtain the following characteristic equation, which is lambda coming from here, minus a from here, minus b, e to the power minus lambda to the epsilon from here. So this is tau1, and minus this term coming from this feedback term. This is typical characteristic equation for delay system. This is coming from first delay term, from the second one. And the roots of this equation, the solutions, lambda, will give us the stability properties, the eigenvalues. There are infinitely many roots because it's an infinite dimensional system. And this is a question how they look like for small epsilon parameter. Okay, and so firstly, let's discuss. Actually, there are different roots of this equation. And the first class of solutions, which we call strong spectrum, are solutions which, for small epsilon or for large delays, are independent. So they converge into some constant, which is independent on tau1 and tau2 on epsilon. And the real part of this constant is positive. So let us substitute it here, and we see that if we substitute the constant here, so in this term, then we see that constant has positive real part. So this is negative with minus and divided by a very small number. So it's very big negative number. So this goes to 0. It's very small. And the same with this. So this term also very small for small epsilon. So this means that these terms can be neglected. So they are very small. They don't contribute. And we get that lambda is approximately a. Yeah? So without this is lambda approximately a. And this means that this spectrum exists only if real part of A is positive. So, because we assume that the real is unstable, right, for instability. And it's more or less clear. If the instantaneous part is unstable, the real part of A is positive, then we have also this eigenvalues in the limit of long delay, where the delays doesn't play a role at all. So we call it strong spectrum. And why? Because somehow, in this case, the instabilities, they grow like e to the power at. This is the eigenvalues. And this instability is faster comparing to delay interval. You remember, delay interval is large, and this is of order 1. So it means that on the time interval of order of 1, our perturbation grows fast. So delay doesn't play a role here, and they are not involved, both of them. And I would say this observation is already known, and there are many interesting things connected to these observations. I first wanted to write names, but was so many that I decided to just to mention groups in Berlin, in Florence, in Würzburg, in Palma, in Exeter, and I have seen also a recent paper of the group from Würzburg, Ingo's group from Palma, and Ido Kanta, where the strong instability of chaotic attractor is studied in a couple of networks. So this strong instability has also different names. It was called strong chaos, or it was called also anomalous spectrum in the literature, or Wolfgang Kinzel called it sublaw exponents. Unfortunately, there are still different names for almost the same things, and we have to think how to converge. But this notion has been very useful and applied to chaotic systems and periodic systems. This is, of course, just for fixed points. Okay, so this is about the solutions of this equation, which does not change with tau. They converge to some constant, and they lead to strong spectrum. Assume now that we doesn't have this condition, so that real part of A is negative, so the instantaneous part is stable. So what can we have there? We have this equation. So this is a condition that the strong spectrum is absent in this case, but the instabilities can still grow on the time scale tau 1. So they grow now not so fast, but slower with this time scale. And what does it mean? It means that there are solutions from this equation which we can call tau 1 spectrum, which has this expansion. So what does it mean? It means that in the leading order, the real part is 0. So we have just imaginary part, which generically there. But we can have corrections of the order of epsilon or 1 of tau 1. So this means of tau 1 scale, where you have a real part and imaginary part. And now the real part, gamma 1, will control the instability. Tau 1 scale controls the instability. And we can plug this equation into this equation and look what happens there. If we plug there in this equation, one can see that now the second term will not play a role if gamma 1 is unstable. So if there is instability on that time scale, then this term will not play a role because, okay, if we substitute it here in this term, so the 1 order of epsilon will be cancelled, but the 1 epsilon is still there. So it will be gamma 1 divided by epsilon. Since gamma 1 is positive, epsilon is small, so it will be again exponentially small number. So this doesn't play a role. And this means that if we have tau 1 instability, again tau 2, this term doesn't play a role. Okay. Substituting this here, one can even obtain the expression for gamma 1 explicitly. So let's substitute this here. We get, instead of lambda, I omega 0, plus epsilon term, which we neglect to the leading order. So here should be plus epsilon, but we neglect it. And then minus A, minus B, and then I substitute that instead of lambda, minus gamma 1, and some exponential with imaginary argument. Okay, so this is equation, approximate equation for gamma 1, which can be explicitly solved. You see, if we take this to the right and take the modulus, then this term, not very nice term, which is oscillating, will give us modulus equal to 1. So then this term will disappear, and we can solve with respect to gamma 1. And then we get this equation. So this is how the tau 1 spectrum looks like. It's a function of one variable, so it's a kind of line in the complex plane. And we can look when this line is unstable or stable, when tau 1 spectrum is stable or unstable. And actually, it's again this line is missing, so it's division. So actually, one can see very easily that if the modulus of B, so the feedback rate, tau1 feedback rate, is larger than the modulus of A, the instantaneous term, then we have the instability. Then gamma 1, it means some positive values. One can plot these functions and see it. And so this is a condition for tau1 instability, where tau2 does not play a role, and the instability grows on a time scale tau1. Okay? And this is a single delay dynamics. So this is effectively what happens if the system has one long delay. Another delay doesn't play a role at all under this condition. And this is also happens to be very useful. We call it pseudo-continuous spectrum, but also this can be done for periodic solution, for chaotic system, and for chaotic systems, such instability is called weak chaos. Weak because this is a more slow instability rate on the delay intervals. Okay, so this is again tau1 instabilities. We would like to have tau2 instability. So we would like to have a situation when a second delayed feedback plays a role. Here it's not important, we can neglect it at all. So let's look for the condition when it is the case. And of course this should be inverse of this condition. Because when this is the case, then we have tau1 spectrum positive. If here say inverse inequality, then we doesn't have tau1 spectrum, and tau2 feedback plays a role. Okay, so these are conditions. Okay, the first condition was the condition for absence of the strong spectrum, fast instabilities, and this is the absence of tau1 spectrum. Actually, there are quite natural conditions. Yeah, you see the real part of A, the stability of instantaneous terms. This means that tau1 feedback term is not too large, and here one can see. So in this case, indeed, the instabilities can grow very slowly on the tau2 scale, so on this time scale. And following our approach, what I was telling previously, we can try to look at this expansion. The same idea, first order terms only imaginary, no growth rate. First order term in tau1 scale, only imaginary part in the spectrum, so no growth. And only here on the tau2 scale, when epsilon square, we have a real part which can create the instability of growth. And that now this should be plugged into this equation, and in this case, all three terms will be important. They will be non-neglectable, and so all delays are working now, cannot be neglected, and explicit expression, similarly to the previous one, for gamma 2 is also possible. It's not important, of course, for us now to follow the derivation, but just to understand, we plug this into the equation, and we can find explicitly gamma 2 as a function of omega 0 and omega 1, as a function of that and that. It's not so complicated, but still doesn't important now for the understanding. And this is a tau2 spectrum, and it's important that now it's a function of two variables. So one can also show that in this case all the eigenvalues, they are discrete values, but they converge to some two-parametric family, which can be parameterized by omega 0 and omega 1. Yes. And this surface has, due to this simple formula, has very simple properties. It's just a surface with a single maxima, and this maximum can be found, I guess, on the second picture. This is just schematically what we have. This is just a repeating equation, characteristic equation. And this is what we have for the spectrum. Once more, the spectrum is discrete. There are a discrete number of lambda solutions. but they are densely sitting on this surface, of this two-parametric surface. We can parameterize them. And the maxima of this surface is just logarithm of modulus C divided by, it's hardly visible, modulus of A minus modulus of B. So it can be very simply computed. The maxima, so the instability can be simply found. Yeah? If the surface, the whole surface is negative, so we see here that the real part is negative, then we have stability. If it becomes positive, then we have the instability, which is introduced by two delayed feedbacks.
Omega 1, omega 0 are to be determined or are parameters?
These are now as free parameters for us. They, for a finite delay, so let's say if we choose epsilon 0.01, yeah? Then we have finite omegas, finite values of omegas, but there are many omegas which are very densely located. So somehow we have...
You fix omega 1 and you get the value for every...
No, we have some... in this two-dimensional plane, it goes a bit in a technical side, but anyhow, maybe I will try anyhow to say. In this plane, omega 1, omega 0, there are also, it's not a continuous, there are points which correspond to solutions, but one can show that the smaller epsilon, the denser the set of points. So there are very dense set of points which can be approximately said as continuous. And then the eigenvalues are just the values on the surface which correspond to this. Yeah. So this is approximated by the surface. Okay, and very roughly, it's maybe it's a bit complicated, but if you try to get some intuition, omega 0 can be considered as a delay-induced Fourier modes with respect to tau 1 scale. Omegas 1 are delay-induced Fourier modes with respect to tau 2 scale. It's a bit complicated to understand it, but maybe it's just like analogy. I want to go into PDE equations now, PDE understanding.
I don't see the interplay between the two time scales. So it seems to me that this type of analysis will be the same if the first later was not there. So imagine B is equal to 0.
If the first...
imagine B is equal to 0.
If B equal to 0, then this will be C divided by A.
So what is the interplay between the two? Why do we need two time delays?
If we have no tau 1, then we don't have omega 0. So we will have just omega 1 and gamma 1. So we have one-dimensional line.
Yeah, but you will have an instability on the tau 2 scale.
Yes, on the tau 2 scale, but we have one line, one-dimensional line. We have...
it doesn't play any role in instability, right? Because it's imaginary. It doesn't play any role in instability of the tau 2 scale.
Yeah, it's like you can have the instability which is caused by one-dimensional line spectrum, or you can have instabilities which are arising from two-dimensional lines. Maybe I will say now something about connections to PD, and then I comment again on that. So, and then gamma 2, I remind, it's just proportional to a real part of lambda. So it's a contrasting. And so one can look at the maximum of gamma 2 of this surface and see that the destabilization occurs when logarithm of this argument is 1. So when modulus of C equals to modulus of A minus modulus of B. So this is a destabilization condition. And if you see this tau 2 feedback rate is not too strong, so it's smaller than that, then the system will be stable, again, also with respect to gamma 2 perturbation. If the modulus of C is bigger than that, then it becomes unstable. And now all delays are involved. So this gamma 2 max is bigger than 0. Okay. So just to remember, I will use it. So that's why the main perturbation parameter which I will use is a difference. Yeah, C minus this. So if it's positive, then we have destabilization. If it's negative, we have stability. Okay, and now what is the idea I want to go into? That this is two-dimensional surface which governs the destabilization is very similar to a two-dimensional dispersion relation which exists in PDE, in pattern formation for Ginzburg-Landau, for reaction diffusion system. It's over there. If you have some PDE on a two-dimensional spatial domain, you look for the stability, and this surface, which describes the stability of Fourier modes in one and another direction, the stability of each Fourier mode, will give you also two-dimensional dispersion relation, similar to that case. And again, if you have a PDE in one spatial dimension, just with respect to your question, then you have one-dimensional PDE and you have a dispersion relation which is one-dimensional. And this is a difference. Here we have two-dimensional surface of eigenvalues and it's equivalent to two-dimensional dispersion relation. If we have just one delay, we would have just a line as one-dimensional dispersion relation. And this is a difference now. Our system will describe the destabilization of two-dimensional, the types of destabilization which exist in two-dimensional PDE. And if we have one delay, it's only one dimension. This is the difference. Okay, so it was linear system. But if we go to nonlinear system, what do we do? Now, of course, nothing is possible in such an exact way, but we have some ideas which actually borrowed from pattern formation theory for PDE, which can be used here. And first, the idea is if the linear part is unstable, then nonlinearity should saturate it. Of course, physically it's important that solutions not go to infinity, but just bounded in some domain. This is the role of nonlinearity. Second, we assume that the bifurcation is supercritical. So it means that if our zero steady state become unstable, then close to the bifurcation, some small solutions appear in the nonlinear system, like in Hopf, supercritical Hopf bifurcation. It's the same idea. So that means that nonlinear solution still feels the linear properties, but just saturated with nonlinearity. So this is supercriticality of the bifurcation. And it's actually natural to assume this in this system because we have a normal form for the Hopf bifurcation, where supercritical Hopf appears. Okay, and we expect, as I said, we expect small amplitude solutions. So we look for small solutions, like in the supercritical Hopf bifurcation. And that's why, like in the supercritical Hopf bifurcation, we expect that some kind of normal form would be able to derive some kind of normal form which describes the behavior of the solutions close to such bifurcation, like for the Hopf. And okay, the question, how to deal with delays when deriving this normal Hopf. We will use for this different timescale approach because delays are acting on different timescales. So this is timescale approach. So main ingredients at the end, what do we have? We have, due to deal with different delays, we have to use multiple timescales. That's why we just take the following ansatz, which just means that instead of z of t, our solution, we look for a solution with different timescales, epsilon t, epsilon squared t, epsilon. So different timescales are now in different variables. You see where different variables are coming from. Here's just one. Here there are many, but each of them correspond to its own timescale. And we assume also closeness to the destabilization. So close to bifurcation in order to see small solutions. For this, you remember I introduced the parameter of destabilization, P, which is you remember, governing the maxima of this two-dimensional surface. And we assume that this maxima is small enough. It's just very close to the destabilization. The choice of this epsilon square, it's a bit technical. I don't want to say on this, but this is the smallest. And another point that our solution is small is this epsilon. So you see that these are really small amplitude solutions. So all these assumptions are here in these two expressions. And actually, this is everything which we need formally in order to derive the normal form. This is our equation, tau 1, tau 2. The smallness parameter here, the multiple scale approach, and now it's very technical. Of course, I will not now tell you all details now. We just cook. Yes? We just substitute, actually. We substitute everything into the equation and look for this different order of epsilon. And we require that equation to epsilon to the first order equal, and epsilon to the second equal, and so on. And so it's enough here to consider till epsilon to the power 4. There are some different difficulties with boundary conditions, but these are technicalities. At the end, we obtain the following equation. It's a bit complicated, but very general. I will write down now simpler on the next slide. But what we obtain, instead of this general multi-scale approach, after this comparing different time scales, we arrive at this function. So this is instead of u now phi. And we have seen that instead of this 1, 2, 3, 4 time scales, we have now 3. So somehow one time scale moved away. It's actually a drift, which is a propagation just of some structures. But this is a bit technical. Somehow this is a result how this multiple scale ansatz will come out as a result. And what we see is the following. And this is an equation which function phi should satisfy. So if phi satisfies this PD, then Z is equal to this. So this is a relation between solutions of delay equation and solutions of PD. And you see that theta, the first argument here, is pseudo-time. This is a variable which describes the evolution in the PD system. And this is the smallest scale, which is epsilon to the power 4. Very, very small time scale in the delay system. The spatial coordinates, x and y, here you see the derivative with respect to space, up to the second order. And the spatial coordinates are just epsilon t with some correction, and epsilon squared with some correction. And this is nothing else as tau 1 scale. You remember, tau 1 is 1 over epsilon. So it's this divided by tau 1. So this is tau 1 scale, and this is tau 2 scale.
So what's delta?
Sorry, this is a constant. Just a constant which can be explicitly written in terms of AB. Yes, it's just a constant. Good remark, yes. So it's everything explicitly written. Okay, and this is just a PD, and you see there's a nonlinear term. Actually, this is a Ginzburg-Landau type PD, and in the simple case, I write it in the because this is actually not simple, still very complicated. But in this case, if tau 2 divided by tau 1 is integer, but still large number, and the arguments of A and B are 0, so these are real numbers, we obtain a very symmetric Ginzburg-Landau equation without first order derivatives. This is Laplace operator and temporal. And what is more important, the periodic boundary conditions. So they are translationally invariant with respect to space. So more or less the simplest possible PD in this case. And now let us try to understand once more what does it mean. this was our relation between Z, the solution of delayed system, and phi, the solution of PDE, two-dimensional. And okay, here I don't write delta now. These are constant C1 and C2, just some constant which are explicit. And once more, let us try to understand what does it mean. First, if we have a solution of a PDE, this is a function of three variables: pseudo-time, pseudo-space. How to get solutions of delay equation? It's very simple, actually. We just evaluate z of t, we just evaluate function phi along the line. So we just substitute this. But geometrically, it means the following. Theta, this is the pseudo-time variable, is like that. X is this first one, and y is the second argument. And we have to look modulo 1 because this is the domain where we consider. So we have to wrap every time when it meets 1, it goes back to 0. And these are, in a three-dimensional space, lines. So you see this is linear in T, it's just parameterized with T lines, which are for small enough epsilon cover densely this three-dimensional space. So it's just geometrically how it looks like for epsilon 0.05. These lines are really densely filling the space x, y, and theta. And if we have the solution of PDE, we just move along the line and evaluate this function in this point and get that, our solution of the delay system. So this is how one can imagine the interpretation. If one have PDE solution, how one can get Z of t geometrically. Very simply, it's just evaluating on that. But how can we go back? How can we get a solution of PDE from the solution of delay system? Actually, it's known as a special temporal representation of solution of delay system. You know, it's known for a while already. People use it, especially for one-dimensional. The special temporal representation of the solutions of delay system. So in this case, it would formally mean how can we get phi from the known solution Z of delay system. And this is just inverse. Yeah. What we know a value of our function along the lines, which was introduced before. That we have this line. We know the value of the function along the lines. And the lines, if epsilon is small, they are very dense here. So the distance between the line is actually for epsilon. The smaller epsilon, the more dense. So we can actually, knowing this information, we can extract now a continuous function phi by interpolating, for example. So what we do, we just fix theta, for example. This is a pseudo-time. Take a small layer and interpolate within the layer for a given theta 0. And we get a two-dimensional pattern. For example, it looks like that for a given theta. And then we change theta pseudo-time, and we will get another pattern. So we will get a set of patterns we get moving. We have changing two-dimensional patterns in this way. And so they will change with theta, and as a result, we will get special temporal representation of our solution. This is how one can do this, how we did in our results. And this is again coming back. This is what one obtained after a special temporal representation of such a solution. And you see these are two very nice coexisting two spiral defects. So this is just for the amplitude. And in this case, one can get very clear defect turbulence. These are solutions of delay system. It's not PDE, but the PDE looks very similar. That's why I don't show it. It's really like almost the same. And now I would like to comment on the generality. Why spiral defects and why defect turbulence? Why not something else. For this, let us come back to a known classical paper of Chateau and Melville, where they plotted this two-dimensional, let's say, parameter diagram for two parameters. This is an integer part of a diffusion coefficient for this term, and real part of minus d of this one. And they observed that in this plane of these two parameters for this PD, one can observe in this defects, spiral defects which I wrote here. In this domain, one can observe defect turbulence, and somewhere here also phase chaos. But in our case, the diffusion coefficient, 1 over modulus of A, is always real. So in this parameter diagram, we always have imaginary part 0, so we are on this line. So that means we don't have phase chaos, but we have frozen defects and defect turbulence. Generically, we should have it there. So that's why changing the real part of D, we took just 1 point from turbulence. And this is exactly matching the dynamics as well. So this is kind of generic things which one can expect at all here. So this is what I said, diffusion coefficient is real, and one observed two different behaviors just varying the nonlinearity parameter D. This is the same parameter which we have in nonlinearity in delay equation. And finally, okay, this is the same. Just the picture shows additionally a plot of the contour lines for the phase, just to show that at this point, when the amplitude goes to 0, we have that the phase is not defined. This is how defects look like, and they coexist. Okay, that's the same. Just to remind, now I hope we understand it more than before at the beginning. Absolute value and real part. And for the defect turbulence, we see more defects here. And if one look on the dynamics of this defect, it's more or less erratic, it's chaotic. So that's why it's called defect turbulence, Ginzburg-Landau setup. And this is, again, once more, this is delay system. This is how defects look. And finally, I would like to show, this is still a Ginzburg-Landau, this simple system. Finally, I will react till the end picture. Okay. Yes, I don't know why it doesn't react. Should be till 2. Oh, yes. And again, this is the phase for defect turbulence. And you see first, after some transient, the defects become erratic, and they interact, and the behavior is very complicated in comparison with the spirals. And what is left for me, sorry for 5 minutes of delay, I would like finally show the same effect which we observe for Landau-Yanchuk type system, with two delayed feedbacks. And this is the system with two delayed feedbacks again. And this is just a snapshot of a spiral defects. It's a bit more deformed, but one can see clearly two spiral defects which on the phase plot were clearly identified. For those who are dealing with, who knows pattern formation theory, one can observe also lines overlapping with some stripes, but still the defects are there. And this is a turbulence, which in a video, this is a defect case. There is some erratic transient, and then very clear two defect points appearing and stabilizing. And stripes, of course, they look like moving, but still the defects stay somewhere. This is how defect turbulence looked like. Interestingly, it was very easy to control this by alpha factor, which is in the Blanco-Bayashi system. And if we increased alpha factor, we observe turbulence. For smaller alpha factor, we clearly observe spirals, defects, and distance. So nice, can be nicely traced to physically relevant parameters. And to conclude, so we showed that systems which with delays which are from different time scale, they can show some generic types of instabilities which can be used studied by normal forms. So we do expect that arbitrary systems with two hierarchical delays will develop such types of instabilities. And the high-dimensional spatial temporal patterns are encoded into dynamical behavior like spiral, defects, turbulence. Maybe something else, any ideas would be interested, like line defects, whatever. Any patterns we could try to look there. They are relevant to optical systems. Maybe some other examples would be interesting, hierarchical networks. And so finally, I would say that there is a preference with Thank you very much.
Thanks a lot for the fascinating presentation. Time for questions. Yes.
Yeah, so you do this mapping, and then you say that you can have defects and turbulence and so on. What can you learn from this when you go back to the real setup?
Yes. For example, one can understand the statistic. For example, the distribution of intensity for the lasers. If you see some erratic behavior, time series, you can think about the statistics, how long the laser stays in the state with a high intensity, or how long it stays with a small intensity. This is power distribution. And the distribution in this case, when we know that this is a defect, we can immediately get the formula for this statistics and scaling for different delays. So it can be done. And in our paper, we write down. So we basically we know the features of the system. We know how many times it goes to zero or something like that. So we can qualitatively explain many features of the behavior. Type statistics.
More questions?
Yes.
The pseudo time in the spatial temporal system, does it correspond to the fastest time scale of the delay system or the longest time scale?
It's the smallest, yeah, the longest. It's even tau.
That means the individual frames that you have in these simulations, they are, so to say, in repetitions of tau 2.
Yes.
Okay.
Yes.
Yes.
So in the spatial temporal representation, is exactly tau 1 and tau 2? This case, and you repeat the structure.
Not exactly. There's an interesting question. If you do exactly tau 1 and tau 2, you will get a very fast drift. You will see also the frames which look like that, but what you will see, they are moving just very fast. And in order to see the Ginzburg-Landau dynamics, you should eliminate this drift, so you should correct it a little bit. So it's not exactly tau 1, it's tau 2, that's from the formula. Hopefully, no.
That's the same as in 1D spatial temporal representation.
Yeah.
You also have to compensate for the drift.
Yeah, I just want to show the formula because in this function phi, we have the arguments which are not exactly epsilon t, epsilon squared, but some corrections.
And then the periodic boundary conditions you mentioned very rapidly that was indeed periodic. But then you have a regime which is turbulent. How is that periodic?
It exists? Or
So it is truly periodic, in the spatial temporal?
In space, periodic in space.
Yeah, exactly. So you say in the temporal system is chaotic, while it has turbulence. And then you put this spatial temporal representation, this is exactly periodic.
No, it's the periodicity in space. So it means that in this picture, that line should come somehow here somewhere. Or this line should meet somewhere here. I don't know. So this is wrapping, so it's dynamics on the torus. But this dynamics can still be chaotic. In time.
And it is truly periodic it's rigorously
in space.
In space, yeah.
Yes. It's, yeah.
So it is in space and time, because from corner to corner you have gone from tau to tau 2.
Exactly. Usually you have an offset of 1.
Yeah. Well, as I thought when I understood, this representation is only good for periodic solutions, or strictly speaking, is only exact for periodic solutions or within time, so that you get exactly the periodicity of the space.
No, this also for chaotic, and I think the turbulence is a chaotic state, and it's here. Everything happens on different time scales. So the periodicity in space doesn't mean the periodicity in time here.
So you explain what the look, and then there are something's going on in the border or something like that.
I have to think. Like in the Ginzburg-Landau oscillation, you have periodic boundary conditions, but still you have curves.
No, yeah, of course. Yeah, I understand that in the Ginzburg-Landau. I don't understand in the spatial, in the temporal domain. Exactly.
So roughly it would be like that. You have if you look on the smaller time scales, like of order of tau 1, then you see some repeating pattern, like periodic. But they are not exactly periodic, but to some approximation periodic. But then you look longer on this pattern, on this pseudo time scale of the Ginzburg-Landau, which means it's very long, then you see that they eventually become very different. So they are chaotic on a very long time scale, but as you zoom, it looks like they repeat almost periodically. So this, I would interpret it like that.
You use very different time scales for this representation. So one is 1 and the other is also epsilon square or 1 over epsilon square. Do you really need that big separation of time scales to the condition?
Yeah, I mean, for everything which I did here, we really need this time separation. And it looks like, in order to see high-dimensional spatial dynamics, one should have time scale separation in order to get them independent spatial variables on PD. If one would say, for example, tau 1 is very large, but tau 2 is 10 times tau 1, then this is effectively like one long delay, which is not exactly, but this doesn't work. Yes.
And with the boundary conditions, the systems you get that does not have exactly periodic boundary conditions, that one line is typically mapped to the next one. Because those are the original periodic boundary conditions that came from the delay system. So it is like a torus, but where you have cut the torus and shifted in one direction by connecting, so by one grid point or whatever, so whatever the displacement which is proportional to the depends on the delay. So that is affect the dynamics that you should observe. I mean, the periodic boundary conditions are not periodic.
No, we have really periodic, and this offset which you mean, this offset which you mean is included in a drift. In what?
Oh, okay. So it's taken out.
Yeah, we include it, incorporate in the equations as a drift, and then we have periodic boundary.
Okay, so this is perfectly periodic boundary.
But only for some situation. In general, we have a boundary conditions with some additional rotation.
Okay. And now, if the strength of the two feedbacks is different, is that like a Ginzburg-Landau with some anisotropy?
So,
if the strength of the two feedbacks is different,
yes,
very different, would that be equivalent to a Ginzburg-Landau with anisotropy in the direction? So that the coupling in one variable is stronger than in the other, along the other variation?
This is interesting question. We have to, I didn't look at this. I think that would be looked at the equation in order to move forward in this aspect.
Okay, final question?
One more, just computationally, what's faster, integrate the delay system or the
It depends. For me, it was more simple, more easy to compute delay.
The delay system was
Yes.
simple.
Yes. But it's for me because I have more experience
Yeah.
with it. Maybe for PDE, for people who have experience with PDE, it would be faster. But to know, if one speaks about experiments, then maybe experiments with laser with delay would be faster than some delays of Jacomelli.
The delay, you can use the delay system to simulate PDE.
Yes.
Emulate, not simulate. So let's thank Serhiy again. You can find it during the next month.
Is there